Everybody, so my voiceover recording did not work and the audio got lost through this video, but instead I'm going to do voiceover. So today we are going to be looking at two examples of a rectangular slab with a cross-section area. We're going to look at those initial conditions, and then we're going to use a coffee cup example. So let's get into our first example here. So we have one side that is perfectly insulated. So here we're going to draw this out. And it looks like I am struggling a bit to draw this out. So this is the side of our cross-sectional area A, and this is going to be the side that is perfectly insulated. And then this is going to be our position x equals 0, and our position x is L at any length. This is going to be the side that is exposed to the air. So for our insulated, we're going to show that T at position x at time equals to 0, so at our initial conditions, it is 80 degrees Celsius. And then for the air, which is position 0, at any time the temperature is 20 degrees Celsius. This is going to be showing our height of our slab, which is going to be denoted by H. And so we're going to show you how we can use heat equations. So we're going to have Q of conduction of our insulated surface is equal to the negative thermal conductivity coefficient times the area multiplied by the time relationship between temperature evaluated at x is equal to L. We can denote that this is negative because we are going to set up our positive axis for x going in the right direction, because we want our heat flow to go from hot to cold, 80 to 20, going in the opposite direction, which is left. So that will keep being a negative sign. We can say that our net accumulation is equal to 0 because there is no change in energy. So we can set the Q conduction of our insulated surface equation evaluated at x is equal to L completely to 0. Next, we're going to look at the side of our air, which is Q convection of our air-sided surface is going to be the height multiplied by the area, which is our cross-section denoted by A, multiplied by the time it takes for air, which we have as infinite time, or the temperature of infinite air, minus the temperature at x is equal to 0. We have our air minus the surface of our slab. So we can set that equal to 0 as well and make it equal, or we can set that to our negative K, which is our coefficient, or yeah, our thermal conductivity coefficient, and this is temperature over time, and that will be at position 0. So now we are going to draw this out on our curves. We have our graph of temperature versus time on the x-axis, and we split these into several sections to show each of our. So we have our air next, and it is guarded by the left side, which we denoted as x is position 0. The right side of our slab, which is x equals to L, and then we have our insulated, or our insulator. So, whoops, did not mean to do that. Okay, and then our heat flux across the insulator is not changing with respect to time, so this derivative, or the slope, is going to be a straight line. And then as we cross from position x is L to x equals 0, we're going to have a drop, but the steepest drop is going to be from the left side to air, and that is because the biggest change in temperature between is going to have the steepest drop. And that's denoted like there. And that is how you can show your initial slab conditions on a temperature versus time graph. Okay, so one way that we can go into this a little bit deeper is through the idea of a coffee cup. So I'm going to have it modeled as such. So this is going to be our air. This is going to be our coffee. And then we're going to have a glass. And we are going to have an insulator slate. Okay, so we are given that the temperature is a constant at 90 degrees Celsius, so we can write that here. And the outside air has a temperature of 20 degrees Celsius. In terms of position, this here is going to be our our length of the insulator. Oh, geez. Okay, there we go. Length of insulator. And this across here is going to be our length of our glass. So how thick these two layers actually are. We modeled it this way because we are going to say that our x-axis is pointing in the right direction for positive, because our heat is going to go from our heat is going to transfer from hot areas to colder. And so we're going to keep it going in the right to left direction. Okay, so between these, we can model that our heat from the coffee to the glass is convection. And we can write that down here as the Q convection for our coffee is equal to the height, which we will describe as H, times the area and the relationship between temperature and time, evaluated at X equals length, which is going to be X equals L here. So what our coffee is going to move, or the heat is going to go from our coffee to this boundary layer. And we're going to say that this right here is T1. So we can model our heat of convection is going to go from H times the area multiplied by T infinity of the coffee, because we know that the temperature of the coffee is constant no matter what the time, minus the temperature at position 1. So I'm going to move this arrow up just a little bit so you can see. Temperature 1. So next we're going to have the heat transferring from our glass to our insulator. And since these are touching, it is going to be by conduction. And let's clarify that to be convection. Next, we're going to have the Q of conduction of our glass is equal to the negative, because we established which direction our positive X is, and then the heat is traveling in the opposite. The negative coefficient of thermal conductivity multiplied by the area and the relationship of temperature over time, evaluated at L glass. And then we are also going to have the heat loss from the insulator to the air, which is going to be by convection. Okay, and from T1 to T2, so the coffee hits the boundary of the glass, and then it has to move through the glass until it gets the insulator. So between the glass and the insulator, we are going to have T2. And we're going to show that the heat touching conduction is going to be, for the insulator, modeled as the very similarly the negative coefficient multiplied by the area, the relationship of temperature to time, evaluated at the length of the insulator. So how wide or how thick the insulator is going to be. And then as you hit the outside of the insulator, the surface that's in contact with the air, that is going to be our temperature 3. And we are going to show that the heat of the air is H multiplied by the area. And we are going to have T to T3. So we're going to have the temperature, which is always 20 degrees Celsius, minus T3. So I'll make that one pink here, and I will make this one to show that equation. And then we can say that all of these equations are going to be set equal to each other because the net heat flow is equal to all of the heats at each of these surfaces. And so let's set those equal to each other. We're going to have Q is equal to, we have the first Q convection, which is the height times the area, the constant temperature of the coffee, minus T1, which is equal to the second, which is going at the surface of the glass. So we're going to have the negative coefficient times area. And we are going to say that this is T infinity, so the temperature constant of the coffee, minus T1 all over the change in time evaluated from the length of the glass. So we can set all of these equal to each other because we're going to say that the total net heat flow is equal to each of these individually at each point. So we can say that Q is equal to the convection from the coffee. That is going to be the height times the area, and then the temperature constant of the coffee minus T1, which is set equal to the conduction of the glass, which is going to be the negative constant times the area. And we're going to have T2 minus T1 all over the length of the glass, which is equal to the negative coefficient times area. We're going to do the difference once again. So this will be T3 minus T2 over the length of the insulator, which is equal to air, which is going to be the height times the air. And we're going to have T infinity of the air minus T3. And then we're going to keep looking at that and model it similarly to how we did up at the top, but I will draw the curves. Okay, so this is of our coffee. This is of our air. This is glass. and our insulator. So we have T1, T2, and T3. So we know that the coffee has a no change in relationship to time. So time here and temperature up here. And then as it hits the barrier of the glass, there's going to be some heat loss and it is going to decrease. Like so. Let's start on our endpoints actually, so that we can evaluate which curve is going to be steeper. So we know that from air to insulator, you have a pretty decent decrease, and that is our T3. So now for determining the position of T1 or T2, the coffee from the glass is a better, is going to be still a decrease, but slightly less steep, like this. If I can draw better than that. And then the largest difference is going to be from the insulator to the air. So that's going to have the steepest. And that is T2. So there is how you can model. Okay, so this is quite a bit to look at all on its own. So what we can do is relate this equation here into simpler terms. We're going to say that our heat flux is equal to the height times the area, and we are going to use our coffee and our air because those are the two endpoints that we have. So we're going to have the temperature of the coffee minus the temperature of the air. And we are going to relate this using Ohm's law as an analogy. So we have for Ohm's law, change in voltage is equal to the current times the resistor. And we are going to have two different forms of this equation, both for conduction, and we're going to have another one for convection. So what we can do is say that the change in temperature for both of these, well, let's see conduction first, actually, hold on. So for conduction, the change in temperature is equal to the heat flux times the length multiplied by our thermoconductivity times our area. And our convection is equal to the flux, and it's going to be 1 over the height times the area. So I know that you're thinking, Taylor, how do we relate this to Ohm's law? Well, these two are going to function as if they are our resistance, and the Q, our heat, is going to be like that. So let's look at this in terms of resistance. So we have our coffee, which is due to convection. So this is going to be the resistance of coffee is 1 over the height, which we denoted H, times the area. And then we can look at the resistance of the glass. And as we said, that is due to conduction. So that will be the length of the glass, so how thick the glass is, times the thermal conductivity multiplied by the area. We have the resistance of the insulator, which, as we said, was also conduction. And that will be the length of the insulator. Times the thermal conductivity area. And the resistance of air is due to convection, as we said over here. And that will be 1 over h times the area of the surface. So this is the height of air. This is the thermal conductivity of the insulator, of glass, and then the height of the coffee. Just for further clarification there. And then these are all in a series. So using Ohm's law, what we can say is the total resistance is going to be equal to, and then we'll factor out all of them have the same area. And we have 1 over the height of the coffee plus the length of the glass over the thermal conductivity of the glass plus the length of the insulator over the thermal conductivity of the insulator plus the resistance for air, which is 1 over the height of the air, like so. So this would make it a little bit easier to see how everything fits in. And we can say that it's in series because it directly goes from the coffee to the glass to the insulator to the air as we've drawn it out. And those are 2 examples. We talked about a rectangular slab with initial conditions for one side being insulated and the other being exposed to air. And then the second example was the coffee cup, where we were able to draw out our graphs for temperature and time, and we were able to further explain using Ohm's law. If there are any questions, please leave a comment below. Thank you.